Hello, we are talking about asymptotes again. So first of all, once you get to the worksheet, maybe you've looked at it already, I don't know. But really this is about defining asymptotes with limits. It's not entirely different than what we've done the last couple of days. So a vertical asymptote is defined as the limit as x approaches c of f of x equals infinity or negative infinity. If that's true, then x equals c is a vertical asymptote. And this isn't new, but we'll write it again. For horizontal asymptotes, this is where the limit as x approaches infinity of f of x equals c, or the limit as x approaches negative infinity of the function f of x equals c. And if that's true, then y equals c is a horizontal asymptote. Again, this is not new, but I'm just defining it again for you because I felt like it. Okay, so I'm going to do an example similar to the ones on the worksheet, and our task is to find the vertical and horizontal asymptotes if they exist. And the way I'm going to show you is basically how to prove that it's a vertical or horizontal asymptote. So if we have the function f of x equals 2x squared minus 7x minus 4 over x squared minus x minus 12. So the first thing we can do for vertical asymptotes is factor it. The top factors into 2x plus 1 times x minus 4. And the bottom factors into x minus 4 times x plus 3. The x minus 4's cancel, so there's a hole at x equals 4, or where x minus 4 equals 0. I'm going to put it in parentheses because we don't really care that there's a hole, but it does affect our answers. So now, to find vertical asymptotes, which you've done, we'll take our simplified function, which was f of x equals 2x plus 1 over x plus 3, once we canceled out the holes. If we set the denominator equal to 0, x plus 3 equal to 0, x equals negative 3 is our vertical asymptote. But essentially now we want to prove that it's a vertical asymptote. Before, what we did is check both sides and check the limits. And that's good to do if you want to know the general behavior. But if you just want to prove it's a vertical asymptote, just show that the limit as x approaches negative 3 of 2x plus 1 over x plus 3, basically we need to show that this is positive or negative infinity. So if we plug in negative 3, we get 2 times negative 3, which is negative 6, plus 1 is negative 5. The denominator is 0. And negative 5 over 0, or negative 5 over an infinitely small number, is infinity. So that verifies, since the limit as x approaches negative 3 is infinity. Actually, it would be negative infinity, right? Because it's a -5, but either way, it's not bounded by anything. So then we do have a vertical asymptote at x equals -3. And looking at both sides, approaching -3 from the left and the right would also have given you this information, but this is more efficient. Now for the horizontal asymptote, or the Haas, I guess, huh? Now we'll look at the limit as x approaches infinity of our simplified function. You could have used the original function. They'll both have the same result. So the limit as x approaches infinity of 2x plus 1 over x plus 3. So we're really just going to look at our leading terms. So the limit as x approaches infinity of 2x over x. And that's just equal to the limit as x approaches infinity of 2, which is just 2. Meaning this function has a horizontal asymptote at y equals 2. Again, I would not say this is different from what we've done, but we're putting it together. So for vertical asymptotes, you find it the same way, but instead of checking both sides, you can just find the limit as x approaches the asymptote, and as long as the limit of the function is positive or negative infinity, that proves that it's a vertical asymptote. For horizontal asymptotes, if you can't just straight up plug it in, you can use the leading terms, and that will give you a horizontal asymptote if one exists.